Math 2414, Partial Fractions, Video 6, Case 2, Repeated Linear Factors. In the previous videos, we integrated a rational function whose denominator factored into three unique linear factors. Essentially, what makes them unique is their exponents are 1. But if you notice in this rational function, one of the linear factors in the denominator is not unique in the sense that it has an exponent of 2. In other words, if we were to write out the x minus 1 squared and bring along the x plus 1, we could argue that there's three linear factors, but they're not all unique because these two are the same. Of course, a repeated linear factor will be represented with an exponent. So how does this change things? Well, it changes it in how we set up the partial fraction decomposition. In general, whenever you have a linear factor with a power on it, so let's say, for example, we have some linear factor ax plus b to the n power in our denominator. And let's move that down a little bit. Let's say that you have a generic expression where there's more stuff over here. Then we have some polynomial function up here. We'll just call it p of x. So if we're going to do a partial fraction decomposition and a linear factor is repeated because that has an exponent greater than 1, then we need to set up one partial fraction for every power of that linear factor from its original power all the way down to 1. Specifically, we would need to set up a partial fraction for the linear factor with its power. Then we would need to set up another partial fraction. Let's subscript these numerators. We'll call this one an since it's the power linear factor. And then we would need another partial fraction for the next highest power less than that. So the highest power was n, then we would need n minus 1. Call that a n minus 1. And we would represent every possible power of that linear factor all the way down to 1. So we'll have a constant on top, we'll call it a2, on top of ax plus b squared. Then finally, some constant on top, we'll call it a1 over ax plus b to the first power. Of course, being to the first power, we wouldn't need to write that, but I did want to write, in other words, we could write it like that, but I wanted to leave that on there to emphasize the structure of these partial fractions for the linear factor that has a power on it. And really, this is a generalization for all linear factors, even if the power on them is 1. Because if the power on it was 1, if there was a 1 right here, then we would start at 1 and we would end at 1. So this is really a generalization. Every linear factor gets one partial fraction per power from its highest power down to 1. And if that highest power is 1, like right there on that second factor in our black fraction up there, then it would just get one partial fraction. So whatever the power is, that's how many partial fractions you would have to set up for that factor. So let's see how this one would set up. Starting with the x minus 1 squared, because it has a square, we're going to need two partial fractions for it. Starting with its highest power, which is 2. Then lowering it until we get to the first power, but that would be the next one. The second linear factor in the denominator only has a power of 1, so it's just like before, it gets one fraction. Now, the numerators are still constants, so we can just say a, b. The only reason I use subscripts down here is because we didn't have a specific exponent, so I didn't know what number to actually start it with. All right, so it's really not that much different than setting up a partial fraction decomposition for a rational function whose denominator has unique linear factors. Just keep in mind that whatever power is on that linear factor is how many partial fractions we'll set up for it, starting with the power that it has and eventually working your way down to the first power. Why don't we go ahead and try to find a, b, and c. And remember, the trick for doing this is to multiply by the least common denominator. And in the last video, I tried to squeeze all those multipliers in, and it was a little bit congested. What I think I'll do this time, instead of writing the entire denominator, I'll just put LCD, common denominator. Well, it's really the least common denominators for these guys as well. But we're just going to multiply both sides by the least common denominator. So let's see what that would do. LCD here, LCD here, 1 here, 1 here. Now the problem with doing this isn't on the left. On the left it's easier. The denominator cancels. We're left with 4x. But on the right you have to be a little bit more conscious of what's going on because we didn't explicitly list all the factors. For example, on this fraction right here, there's an x minus 1 squared in the denominator, and so when we hit it with the least common denominator, and I think I am going to write it out to the side just so we can see it. All right, when we multiply this fraction by this, the x minus 1 squareds will cancel. So what will be left is the a and the x plus 1 from the least common denominator. Now, if you're having trouble seeing that, then you actually write all this here and literally cross stuff out and see what's left. But hopefully at this stage in your math career, you can see that without actually having to write it all the time. On the second fraction, the b, of course, would be left. And when the least common denominator multiplies by this denominator, we would only cancel one of the x minus 1s, but we would still have one left over. And the x plus 1, of course, would still be there. So there's the result of multiplying the second fraction. And the result of multiplying the third fraction is pretty easy to see. The c will be left over. And when we multiply the least common denominator times this fraction, the x plus 1s cancel, and that leaves an x minus 1 squared. All right. So we've managed to clear out the fractions, and now we got to figure out what a, b, and c are. Again, as I mentioned previously, there's actually 2 ways to do this, but I'll try to stick with one technique as much as possible. The technique I'm going to stick with is to pick values for x that will cause some of the add-ins to disappear on the right side of the equation. In other words, we want to pick values of x that will make some of these things disappear. Now, here's the problem when you have repeated factors, though. We'll have fewer x values that will cause factors to disappear. For example, for the factor of x minus 1, clearly if x equals 1, that will make that turn into 0. So let's let x equal 1 and see what happens. The left side becomes 4 times 1, which is 4. Here, if we put in x equals 1, we get 1 plus 1, which is 2, times a is 2a. But x equals 1 here and x equals 1 here will cause all that to disappear. So it collapses down to 4 equals 2a, and that immediately implies that a is equal to 2. Okay. Now let's look at the second factor. Let's use this red. 1 second, folks. I'm going to clean up some of the crossed out stuff on this. Actually, I cleaned up a lot of stuff. All right, so let's focus on the next factor in the denominator and see what will make it equal to 0. Well, clearly x equals negative 1 will make x plus 1 equal to 0. So let's see what happens when we let x equal negative 1. On the left side of the equation, it gives us 4 times negative 1, which is just negative 4. X equals negative 1 will cancel this factor and this factor. This plus doesn't look like that real quick. There we go. All right, so as I was saying, putting in x equals negative 1 will make this factor 0 and this factor 0. So those two add-ins will disappear. However, over here, putting in negative 1 will not make it disappear. We'll get c times negative 1 minus 1 is negative 2. C times negative 2 squared, but negative 2 squared is 4. So if you were to divide both sides by 4, you would get c equals negative 1. But we're kind of in a quandary now, because we have an a, b, and a c that we need to know, and currently we don't know what b equals. And we've exhausted all of our x values that will cause the denominator's factors to zero out, since there were only two unique denominators in the factor. So how are we going to figure out b? Well, we can still substitute any value we want for x into this equation that we got when we cleared out the fractions. We only picked 1 and -1 because they were convenient in the sense that they made a lot of the add-ins on the left side of the equation, made a lot of these things disappear, which made it easy to solve for a or c. But there's nothing that says we have to make any of them disappear. We can actually substitute any number that we want, any convenient number. 1 and -1 were very convenient, but now we need to pick something else. So what other number do you think we should pick for x? There's really no wrong answer here. It's just a matter of preference. I prefer numbers that make things disappear, like 1 and -1, but we run out of those. So what should we let x equal? Well, it doesn't really matter, because any value of x will give us something to figure out the b that we don't know. Let's pick x equals 0, because 0 is an easy number to deal with. All right, in the 4x on the left, putting in 0 for 4 clearly gives you 0. So putting in the 0 for x, I should say. In the first add-in, putting in 0 for the x gives us 8 times 1, which of course is just a. In the second add-in, putting 0 for the x will give us b times -1 times +1. So that's just -b. So let's make it a -b. And when we put in 0 for x here, we get c times -1 squared, but that's just +c. And it looks like we're kind of at an impasse because we need to know what b equals, but this equation currently contains a and c. However, we know what a and c equals. A and c, a is equal to 2 minus b, and c is equal to -1. So all this is equal to 0, and if we were to solve that, let's just take this up here. 2 minus b minus 1 is equal to 0. Well, if we combine like terms, 2 minus 1 is 1. 1 minus b equals 0, and it's fairly transparent that b is equal. So when you have more fractions than factors, because of the powers on the factor, then you will not have enough x values to find all the missing numerators instantly. At some point, you're going to have to do something like we did in the last one, where we picked a random value, substitute it, but we also used previous information, namely what a equals and what b equals, what a and c equals, along with that new equation to figure out what b equals. So let's just summarize on the next page what this final partial fraction decomposition is. I've copied the important things from the previous page. The original fraction that we are looking for the partial fraction decomposition of, set up for its partial fraction decomposition based on the factors in the denominator, and of course the values that we calculated for a, b, and c. That means that our partial fraction decomposition is a is 2, so we'll put a 2 here. B is 1, so we'll put a 1 here. And c is -1, so we will change this from plus to minus. And so if we were integrating this, then we would integrate this instead. Guess what the next video is going to be?